Okay, great. So, um, ladies and gentlemen, dear colleagues, as a chairman of the present jury, it's my pleasure, my great pleasure to welcome you in this PhD defense. Usually, such defense takes place in Mons, in the academic room of the Faculty of Engineering, in order to listen and follow the presentation and the lecture offered by the candidate. Fortunately, due to the COVID-19 crisis and the associated containment measures imposed by most of European countries, we decide to perform this defense remotely. Therefore, you can follow this PhD thesis titled Optimize Replacement of Cutting Tools through Degradation Monitoring Techniques and Residual Lifetime Prediction Models by Mr. Luca Equeter through a YouTube channel. The present thesis is directed by Professor Pierre Dombreux from the Faculty of Engineering from the Machine Design and Production Engineering Unit. Let me firstly introduce the member of the jury. Naturally, I will start with the invited members from foreign institutions. Professor Aldo Atanasio from Università degli Studi di Brescia, Professor Roger Serra from INSA Centre Val de Loire in France, Professor Kondo Ajala from Université de Lorraine in France, Professor Liliane Pitelon from Catholic University to Leuven, Professor Edouard Rivière-Lorfèvre from University of Mons, also Secretary of the Jury, Professor Pierre Dombreux from University of Mons, Supervisor of the Thesis, Professor François Ducobu from University of Mons, co-supervisor of this thesis, and finally me, Professor Georges Grossis from also the University of Mons and chairman of the jury. The present public defense follows the private defense which took place also remotely on the 20th of March 2020. The PhD students sent an electronic version and a paper copy of the thesis to all members of the jury a few weeks before the defense. The meeting began by a 30-minute oral presentation of Mr. Luca Equeter, summarizing the context of the research and the main contribution through proof by the thesis. The presentation was followed by 1¼ hour of session of question and answer, after which the jury deliberated. The members of the jury unanimously acknowledged that Mr. Luca Equeter produced a significant amount of work. After reading the thesis and the answer proved by to the question during the private defense, the jury was convinced that Mr. Luca Equeter has acquired a good mastery of the subject. Consequently, the jury considered the thesis admissible and allows Mr. Luca Equeter to proceed to the public presentation of his work. During the private defense, the jury suggested some minor improvements that could be done for the final version of the text. Mr. Luca Equeter considered this comment and sent us an updated manuscript and electronically a few days before. A printed final version in the university layout is expected to be sent shortly. Therefore, I give the floor to Mr. Luca Equeter for presenting his doctoral thesis to the jury and to the audience.
Thank you, Mr. Chairman. Just in order to make sure that the presentation is clear for everybody, I would kindly request from the jury to ensure their microphone is off in order to make the sound as clear as possible. Esteemed members of the jury, dear colleagues, dear friends and family, thank you for attending this defense. It is my deepest pleasure to see all of you here today. Well, obviously, I don't see all of you, but I see the YouTube numbers, and dear, is it intimidating. Today, I will present my thesis dissertation that concerns the replacement of cutting tools. My thesis benefits from the context of previous theses in the unit, including 4 previous doctorates and in particular, 2 in machining and 2 in maintenance and degradation modeling. And additionally, 2 master students picked master thesis subjects that were related to this thesis. I thank them today, maybe they're watching. So all in all, my thesis constitutes the merging of the 2 research areas of the machine design and production engineering unit, depending from the risk and the material institutes of research of the University of Mons. Manufacturing and maintenance are these subjects. Likewise, the thesis also has a link with an ongoing thesis by my colleague and friend Clément Dutoit, who works on the link between maintenance and quality. We'll come back to that later, but obviously for most of you, the question probably is, why would we even care about cutting tools? Well, the difference between this and this is indeed the wear of cutting tools. We can clearly see here the difference of quality between this surface and the surface obtained with a worn tool. Likewise, the shoulder quality here is clearly unacceptable regardless the tolerances. I machined over 200 of these bars over the last summer in order to gather the experimental data necessary for this thesis. In the process of that machining, I wore 30 of tools. What you see here is a worn cutting insert. The flank wear, which is the main phenomenon in cutting in single point turning tools, when the cutting parameters are within acceptable range, of course, is measured vertically here, and the average value of the length of this worn face is usually denoted VB. This length here is roughly 1 millimeter, and this length is roughly 1/3 of a millimeter. Given this context, the interest for mechanical production industries is clear. The objective is to control the evolution of tool wear in order to be able to replace a tool before producing poor quality. Currently, we're obviously not letting tools go this bad, so let's have a look at the criteria that are used for the tool replacement. In order to know whether it's time to replace a cutting insert or whether we can keep it on the machine tool, the common methodologies are firstly based on the worker's experience. When interviewing machining operators, the answer is often something along the lines of, "I heard it was time to replace the insert." It seems that indeed there is a change of tone in the machine noise when the tool reaches its end of life. A second possibility is to base the replacement on the machining time since the last replacement. This often comes from benchmarking tests on the tool, but most of the time it does not take into account newer versions of the tool coating, or simply the variability in the workpiece material. Finally, there is some tool condition monitoring that is already sometimes implemented. The procedure is then simple condition-based maintenance. The drift in the retained variables is observed until threshold, and that will induce the tool replacement. And then there is also a standard which recommends a value in the case of live testing, 0.3 millimeters in VB. And as I explained, VB is this vertical measurement of the flank wear. So we have 4 options here. The first is empirical and hard to quantify. The second has clear flaws because it does not allow to monitor the specific evolution of tools, and it is based on an average behavior. The third is interesting, but you're just waiting for a value to cross a threshold, and there is no estimate of the tool remaining useful life until this threshold is crossed. So now the last option can be included in that family because we are monitoring the condition of the tool. But it's also quite complex to use because you obviously need to stop the machining in order to be able to measure this value. But it's a quantifiable value, we can measure it, and it's one of the major benefits of this criterion. Now, the value of this criterion says absolutely nothing on the quality of the workpiece that are machined with that tool. Are we assured to produce within tolerances? No idea, but it's measurable and it's standardized. So let's work with that for the moment. So we have a variety of criteria, and the research question that comes from this is, are we able to determine the remaining useful life? In other words, considering the next planned machining operations, considering the specification that must be met on the workpiece we are working on, considering the admissible VB value, considering the current state of the tool, how much time can the tool continue producing? In order to answer this question, we have developed three approaches. The physics of failure, where we represent the degradation of the cutting tool. The condition monitoring, where we monitor a series of variables, forces, electrical power consumption, tool wear, etc., in order to determine clearly, directly or indirectly, whether the tool has reached the end of its life. And then there is the statistical degradation modeling, where based on statistics, we assess the average life of a tool. A first approach consists in the modeling of the cutting process. Simply said, it is the numerical modeling, the numerical simulation, if you wish, of the cutting process. In this model, we will introduce progressively wear on the cutting tool. The objective of this approach is to determine a link between the evolution of the tool wear and some condition monitoring variables that we could measure experimentally. So we are at the junction between both of those approaches. So let's talk a bit about this model. It is a finite element model in which we discretize the model into elements on which we calculate the value of quantities of interest. They may be temperature, stresses, etc. It represents orthogonal cutting, which means that the material velocity is supposed to be perpendicular to the tool edge, so the velocity is horizontal on this figure. The model is in the CEL formalism with a Lagrangian tool, which means that the mesh of the tool is linked to the material. If the material moves, the mesh will move too. And then there is an Eulerian region that surrounds the cutting edge and that allows the material to move in it without deformation of the mesh. So the mesh does not move, the material is flowing through it. So we have the formation of the chip on the upper part here, and the machine surface will appear here. We start this, we let it converge to steady state, and we validate the experimental, with help of experimental data that was provided by our academic partner RWTH Aachen. Then we went on to represent the tool wear by altering this surface in order to represent the wear. So we are peeling away material from the tool in order to create an horizontal surface that corresponds to the tool wear. In this figure, I only represented the part of the mesh where the material is at the beginning of the simulation, but there is plenty of mesh in order to allow the material to move and to form the chip and the machined surface. Then, taking into account the tool wear, a temperature plot allows seeing the influence of the tool wear and to ensure the tool wear indeed has an influence on the model. It's probably difficult to see on your screen depending on the video stream, but this here is the fresh tool without tool wear, and we progressively add wear on this lower face, as I explained. It's easier to see here on the final stage, where we have a longer area of contact between the tool and the surface, where most of the heat is indeed generated. So there's clearly heat generation along the flank wear land, which validates an influence of the tool wear. Then there's always room for improvement, of course, and for example, one could add crater wear to the model. But the objective at this stage is to produce qualitative results, so it's already quite interesting. I also use these views in order to define forces. We name cutting force the force resulting from the cut along the horizontal axis. So the force measured on the tool along the horizontal axis. And we name feed force the perpendicular component, so vertical component. Precisely, this model allows highlighting the evolution of force components, feed force and cutting force, with the tool wear. In these graphs, we have along the x-axis the evolution of the tool wear from 0 to 0.3 millimeters, and along the y-axis, the evolution of force components here, and the ratio between the feed force and the cutting force on this graph. In this case, quadratic linear and exponential regressions are all excellent for the feed and cutting forces, but also for the ratio between these quantities. These results bring forward the importance of forces as a wear indicator. As we will see later with the experimental work, this is confirmed indeed. So let's go back to our triangle of approach. We already showed how we can link some condition monitoring, that are the cutting forces, with the tool wear. Now let's have a look at a way to use successive observation of the tool wear as condition monitoring in order to infer the statistical residual lifetime for the cutting insert. And this is the stochastic approach. In other words, we are going to take pictures of the tool and evaluate the wear at the time and deduce the time during which we can still machine with this tool. So the principle is easily stated. We simulate positive increments of degradation, and the failure time corresponds to the crossing of the wear threshold. In this example, we inspect the current state of the tool at 5 minutes here. We then generate numerically degradation paths that are represented in blue that lead to an estimation of the remaining useful life. When we, short before that planned end of life, we inspect the tool again, and we observe that it is not quite worn yet. So we generate a new set of curves in red and the corresponding RUL estimate. So obviously, the question is, how do we generate those curves? It is based on a gamma process. Basically, the degradation corresponds to the initial degradation, that is the degradation observed at the initial time, plus an increment that follows a gamma distribution. And this gamma distribution depends on two parameters. Regarding these parameters, two models were developed in the framework of the thesis. They differ on the shape function m of t. First, a nonlinear model was proposed using the inflection point in the experimental degradation evolution in its parameters. It is based on a graphical standpoint. A second possibility is the use of a piecewise linear process. With this process, we divide the time interval into slices that I divided here vertically in order to fit for each of these time slices a linear shape function for the gamma process. The parameters are obtained by the maximum likelihood method. The only issue with this method is a lack of data here on the last time intervals. Indeed, if we take this last time interval as separate time intervals as we did before, we are progressively losing curves because the tool have reached the end of their lives before we start this interval. So we are missing data. In order to circumvent this, we can consider the last time as a whole and have a better statistical validity of the fitting. Additionally, for both models, we can correct for the cutting speed, so we can correct the evolution prediction regarding the cutting parameters. In order to put all of this into practice, I created an algorithm that I present here to you neatly, but be aware that behind these simple steps, there are 800 lines of Python codes that are hiding. The principle is, in the learning phase, to fit a linear gamma process for each time interval. Then, we produce degradation trajectories, as I explained, and we deduce the estimated failure time and statistics, and from that, we estimate the RUL, the remaining useful life. Depending on the RUL value, we then either replace the tool or we plan a new inspection after further machining. This method is indeed able to produce an RUL estimate on the basis of few wear observations. Obviously, these observations necessitate the stoppage of the machine and some time for the wear measurement, but we already have something. And then it also needs several tool observations, and more precisely, we showed an important influence of the tool inspection time. All in all, we produce RUL estimates that are roughly 13% below the experimental observed values, but we also showed how this could be used for cost-based optimization. We certainly could also consider an automated image analysis or the use of nonlinear shape functions that would allow to produce more complex shape functions for the tool wear evolution. And we are back to our triangle. So we just showed how we can link some condition monitoring, that is the tool wear at time t, with the tool end of life through a statistical process. Now let's have a look at another possibility for estimating the tool remaining useful life from condition monitoring as well, which allows more choice in condition monitoring variables, since it could possibly take into account any variable that is related to the tool failure rate, and this is the Cox-PH model. I made you once again a nice algorithm that mostly works like the previous one, so I'm not going to detail it step by step once again. Rather, I will point to you this loop here. It actually means that we are able to use the failure data from a previous failure and add it into the model. This means that with the progression of machining, we are actually able to continue training the model over time as tools fail. This was not allowed by the previous model, which necessitated experimental observations of the tool. A last element before we continue. It may seem anecdotal, but it is not. The Cox-PH model is also able to take into account the fact that the tool was replaced before it actually failed. And this is important because it's valuable information and it allows to continue improving the model even though we are replacing on the safe side of the failure. So now let's dive into the model itself. The model allows computing the failure rate of a system. The failure rate is an indication on the failure probability at a given time, given the fact that the system worked until now. You have here the general expression of the model with its baseline hazard, that is, without considering the influence of the covariates, and the covariates and their weighing coefficients. Most of the time, their function is a linear combination of the covariates. In fitting a pH model, it is obvious why covariates must not be linear combination one of another, as the weighing coefficient of collinear covariates would then be undetermined. On the nature of the covariates, they correspond to basically any variable that is related to the hazard rate. They may be time-dependent. They represent parameters that are constant during the tool life, such as cutting parameters during tool life testing, for example. They may also be time-dependent and be able to take into account all kinds of time-varying variables, and especially condition monitoring variables. This is the extended Cox-PH model. It has its complexities, but we will come back to it in a while. I will start with the gentle traditional Cox-PH model, so the time-independent model. In general, the output of the pH model is a hazard rate h of t, which is used in order to determine the lifetime of the tool. The reliability of the tool is computed from the hazard rate, and the idea is then to obtain the mean uptime of the tool, its mean average, from integrating again the reliability. At this point, the first question that comes to mind is whether a data transformation or a normalization should be necessary. The normalization is not necessary as it would be compensated by the weighing coefficients, but we may use it if we try to identify the relative importance of each covariate. The transformation, however, has been questioned extensively, and I produced analytical developments in the thesis that were just published a few days ago and that show why a transformation may be necessary, in which cases, and how to determine which transformation to use. What's interesting is that for some of the possible condition monitoring variables, the analytic information necessary to determine the best data transformation can be obtained through the finite element method that I presented earlier. And this is why it's important to try to get a link, a relationship between the toolware and the condition monitoring variables. The interest of this transformation is shown in these figures. There is a law, the Taylor's law, given here, that links the tool life t with the cutting speed Vc. What's interesting with that law is that when we keep the same tool, we are able to determine the parameters Ct and n, and it allows predicting the tool life t for basically any cutting speed. Well, we can use the Cox-PH model in order to determine these parameters. With the data transformation, we have a significant gain in accuracy of these parameters determination. So here we have the accuracy of the parameters estimate, and here Ct here, with 1 corresponding to 100%, so the exact value. And this is a function of the learning sample size. And we show that the log transformation that we proposed for the data in this case allows an improvement in the estimate of the Taylor's law parameters, hence a better tool life prediction. Now, on the front of the extended pH model, which has never been used, to the best of my knowledge, in the case of cutting tools, it is well adapted to condition monitoring variables, which may be considered as covariates for this model, actually. It is, however, much more complex because it necessitates an estimation of the covariates after the current time. Indeed, we have here in this integral an integral that goes up to infinity. So we need a knowledge of R of t, hence of h of t up to infinity, whereas in h of t we have the covariates that appear. So we need knowledge of values of the covariates that we do not have yet, but we are able to extrapolate a bit and to obtain interesting results. If we are using only the cutting parameters, and if they are planned ahead, however, it is a big advantage because we know in advance what the cutting parameters will be. But indeed, if we decide to use condition monitoring variables, the predetermination may be a bit complex. Now, before we continue, I'm going to make a short pause on the explanation relative to the Cox model. because I need to explain to you what data I gathered to assess this model. As I explained in my introduction, I machined 200 bars for experimental work over the last summer. In order to wear out 30 tools, it was necessary. I did this at various cutting speeds. You have here the cutting speeds for each insert number. And I did this even with varying cutting speeds, as you can see here. You see that for each tool that I wore out, the cutting parameters have been different, except, of course, for the few first batches. Remember, time-dependent Cox model, varying parameters, tools go quite well together, as I explained earlier. In addition, I measured a series of parameters, wear evolution, obviously, cutting forces, electrical currents, workpiece roughness, we will come back to that a bit later, and chip samples. I even sorted the collected chip samples according to a classification of the standard, adding chip subcategories because it was actually missing. In the end, I also showed that the chip type evolved with the tool wear, with specific chip types appearing close to the end of the tool life. In this graph, we have for each chip type the frequency of presence with the evolution of the tool wear, and indeed, some of them begin appearing short prior to the end of life. All right, now that you know what data I'm working on, let's go back to the Cox-PH model. The major difficulty, as I said, is the covariate selection. So we are working with covariates that are time-dependent, and we know little about their evolution. So we start with all variables that show some good correlation with the tool wear. And the Cox-PH model gives out the covariate weighing coefficients here. And also some statistical parameters, and the fitting of the baseline hazard to a viable distribution is made, and we have the parameters here. As you can see, almost all the variables that we measured are included. In the thesis, I cover it more in depth, but here's what we start with. Then we decide to remove the non-significant, statistically speaking, variables with a p-value above 0.05. Then we remove the variables of which the confidence interval regarding the weighing coefficient is undetermined between a positive and a negative contribution. Because obviously, if we're unsure whether the contribution is positive or negative to the evolution of the hazard rate, then it is probably not the best indicator to take into account. And finally, we remove the results that are physically incompatible with the reality. For example, a negative influence of the cutting speed on the tool failure risk, as it is the case here. Indeed, it is proven that a larger cutting speed induces early tool failure. It is shown simply by the Taylor's law that I presented earlier. And that comes from the physics of the failure, and it is not subject to questioning. So this is a physical nonsense and should be removed. And in the end, only one remained. Regarding the experimental results, the Cox-PH model methodology that I developed hints to the limitation of the condition monitoring variables to the force ratio only. The results are comparable with the results from the stochastic approach, except we're slightly overestimating the tool life in this case. But through the psi parameters, we may mitigate this. I covered in depth the quantification of the results of this approach in the text, but obviously these results are a bit less visual. But they have as a major advantage to take into account a wide variety of condition monitoring variables. I strongly insist that the importance of keeping variables, we must keep only variables that physically make sense, because with a data set large enough, it's extremely easy to develop models that appear to fit extremely well, but bear no physical sense with the physical nature of the failure. Here we have tangible effect and physical information we may rely to. In the end, we certainly ended up using only the force ratio as a covariate, and with results that are comparable in quality to the stochastic approach, but without meshing interruption. We can measure the forces online, whereas we only can measure the tool wear by interrupting the meshing in order to measure directly on the tool. Obviously, the choice of covariates is a bit complex, but we also benefit from the possibility of continuing the model improvement over time, whereas the stochastic approach needs additional experimental work with wear observation. So, I could have titled this slide, "So what?" So what should one do in industrial context? Well, the methodology that I presented is useless if you are replacing tools from the machine noise. The first question that you should ask is, what is a worn tool? What criteria make me want to replace a tool? What makes me say I cannot machine any longer with this tool? You should focus first on the quality of your production. My answer, but your opinion may diverge, is that a tool is worn when it is no longer able to machine within the tolerances, within a certain probability. With a fresh tool, of course, it's certain that the production requirements will be met, but over time, the probability will grow that the machining will be out of tolerances. So there is the variability of the tool and the material, and thus the scattering of the time or the criterion value at which the tool must be replaced. In the end, there is always going to be scrap, but you need to set a percentage of scrap that is acceptable by taking into account the cost of a tool replacement and the cost of scrap. Only then should one look for relevant sensors and try to equip the machine. One must keep in touch with the quality criteria for the workpieces if possible, in order to maximize the correlation between the measured variables and the key indicators. This will lead to quality prediction. Then, depending on the observed covariates, choose one of the methodologies that I proposed and apply it to the data. I personally recommend working with the pH model because it's able to continue learning past the first few workpieces. It takes data to build a model, and industrially, it's better to be able to return quickly to production and to avoid losing time and material on benchmarking tests. Finally, one should take into account the planification of upcoming machining operation in the assessment of the tool replacement decision. We should make sure that with the estimated remaining useful life, we still have time to do the next planned machining operation. There is actually a lot to propose in the decision aid here, but I stick to the essentials. I will now conclude by stating again that the thesis is based on a trio of approaches with the use of a finite element model in order to gain, among others, pseudo-analytical information. This information can be used with the original analytical developments that I produced in order to determine the right data transformation to go with the pH model. I also worked on the extended pH model, and all this was applied to experimental data that I gathered through last summer. A quick outlook now to the possibilities of improvement, and I will keep it brief. I'll just mention the possibilities regarding crater wear in finite element model, other possible shape functions for the stochastic approach. Obviously, there are numerous questions concerning the replacement criteria for cutting tools in the industrial practice and the link to the workpiece quality. All in all, this work may be a part of an integrative solution for tool RUL prediction in industrial environments, especially given the tremendous amount of data that will become available in the framework of Industry 4.0. Now, I will just take a short moment to summarize the 4.5 years that just went by, because I don't want this conclusion to stay just a summary of my work. It is 4 years that brought so much more than figures and scientific results. Of course, I had to set out a statistical artillery that I just explained to you, but I had the tremendous opportunity of meeting industrial contacts and international partners. We are working right now with NG and other partners. I had multiple contacts with Colline, for example. I had also the opportunity of having master students working on subjects related to my thesis, Arnaud Ega and Robin de Vlaminck. I want to thank you guys. You're likely watching. Thank you. I'd like to thank you for your attention. But before I answer your question and comments, I'd just like to thank the jury for taking the time to read the thesis and help me improve it. Thank you for your time, your availability, especially given the current sanitary circumstances. I fully appreciate. Thank you.
Okay, Luca. Okay, thank you, Luca, for this presentation, which summarizing your work in a pedagogical way. I will now ask the members of the jury if they have additional questions about this work. Usually I start with the people from foreign country, but as Liliane Pittelon was not available during the private defense, I will ask Professor Liliane Pittelon if she has some question about this work.
Okay, thank you. I have 2 questions I would like to ask, if that's okay, or do we only have one question?
Yeah, for sure, we have time.
Okay. Dear Luca, I've read your dissertation with great interest, and I would like to congratulate you with the work done. The manuscript was well written, nice to read, its content was very interesting, the literature review at the beginning was recommendable, and the modeling work in the later part was original in the combination of the different approaches for estimating the tool's remaining useful life.
Thank you.
Besides the soundness of the theoretical work, I especially appreciated the attention paid to the impact of the approaches developed on industrial practice. And it's related to the latter that I would like to raise a question. I'm aware of the fact that it's not an easy question, but well, today's occasion, your final defense should give us the opportunity to have a broader discussion on the opportunities of your work for industrial practice, because I think it's very relevant even in the Industrial 4.0 context that we are living in now. So I would like to start very early in your text. On page 3, I think it was, where you introduce your research topic and you point out that the need for better estimation of tool useful life is there in practice. I agree with that, and one of the statements you make is that nowadays companies still seem to rely a lot on the machining workers' experience, and that probably this leads to suboptimal decisions. I do not want to challenge this statement. It's all of my experience that experience is variable, but well, solely relating on that experience and capability is not an optimal thing to do. So I have a question. You already briefly touched on an answer in one of your last slides and also in the outlook in your dissertation. So suppose that we have a company that is working now in the traditional approach, and they rely on their workers' experience to replace their tools. But that company is interested in your work, and they say, well, okay, well, maybe we will like to introduce that in our practice, but they still need some convincing, and they would like you to show that it's indeed financially beneficial to do that instead of the way they are working. Would it be possible to set up an experiment to compare your approach with the current practice? To me, it seems extremely challenging, seeing the many parameters involved, but could you do it? How would you proceed if you want to do that? Could you, well, maybe give some explanation on that?
Okay, it is a very interesting question. Thank you for asking it. I tried indeed to cover it a little on this slide, but I will come back to it. The idea is that it is quite complex without having the partner, the industrial person in front of me, the requirements on the machining process as well, to give general recommendations, because I firmly believe this is a case-by-case application. There is a general methodology, but it should be applied case by case. So what can I recommend in general is to first start by taking notes of the tool failures and tool replacements, and especially the reason for the tool replacement. The idea is to start the implementation by having some logs we can rely on in order to start working, to identify the quality problems that are met on the industrial application that is considered.
If I may interrupt, just a
Yes.
question out of curiosity. In your experience, do companies have these logs, or is data availability an issue here?
No, because we are replacing tools basically every 15 minutes, and 15 minutes of machining, of course, but every 15 minutes, and it's time consuming to do this log, and it's complex to go see an operator and ask from the operator to write down what he replaced and why, because it's also on a human point of view challenging.
Okay.
So I think one of the best start is to start with this log. It's complex, but it's necessary. It's necessary to identify the key quality points, and by key quality points, I mean the ones that are most likely to degrade first, so that we can tackle the right failure modes for the tool. Then observe the failed tools, the one that induced poor quality production, because they are the ones who will indicate what kind of wear is problematic on the tool, and if a common level of wear may be identified, and then to work from there by adding the most related sensor given the failure mode that is that is considered here, and work from there.
Okay. So setting up an experiment would be not only company specific, but also in fact task specific, because if you have another task, it might change things.
Absolutely.
Okay. Then my second question, but I think you can remain on that slide, was that the tool's end-of-life criterion PSI is quite important, and during the work several remarks on the factors that influence that PSI were made. I appreciate also that your clarification that you added, because I had a question for the preliminary defense on that, and you added some clarification. I'm still a bit, well, I know it's outside the scope of your thesis, but again, it's a final defense, so we should have the opportunity to dream a bit about future possibilities.
Obviously.
So that multi-criteria approach, I'm very interested in that. What criteria besides cost would you like to include? I would have my first thing would be translate everything into cost. Even quality problems, we can translate them into cost, and well, a tool is a certain cost, so we can replace that. But I'm interested in the multi-criteria that you would use then.
Indeed, I have the tendency to try to translate everything into cost, because at the end of the day, what makes a company live is the question of the cost. And you can translate the quality problems, the availability problems, everything into cost. But I think what what's interesting is the criteria that lay behind this cost. So we have, obviously, as you said, the quality. We have the availability of the machine, because from both of those parameters come not only direct costs, but also other center of costs that may come from them. I explain. If you send to your client a batch of work pieces that are not within the tolerances, or you send it late, you are also going to lose on your public image. And this also has a value, but it's complex to take into account. So depending on the specific case, and I'm thinking especially of airspace industry and so on, you want to focus maybe on quality first, and really give an importance to the quality first, but it's once again depending on the industry itself.
Yeah, I agree. Do you think it would be interesting to have a criterion on the human factor? Because you could say, well, if I have a very well trained workforce, it would be different than if I have all novices, or I don't know, or maybe I have some people that are very quality minded and have people that are less quality minded. Is that something, a factor that you would consider taking into account, or do you think that's too far fetched?
I think it's complex, of course, because we are giving big concepts, but we are not working on a specific case. So it's complex to answer your question. I would answer that it's a bit far from the question, because if we are thinking of the worker's experience, for example, for the noise of the machine detection, then it is obviously extremely subjective observation. So even though people may be trained, it's still complex. If we are thinking of it as a criterion for the replacement of cutting tools, for me, it's obviously not it should not be taken into account, because the person that is operating the machine, especially a CNC machine, would have a relative low influence on the tool failure time, in my opinion.
Okay, thank you.
Thank you.
Okay, thank you. Next, Professor Atanasio, do you have any additional question?
No, I don't have additional question. Thank you for your presentation, very clear, and thank you for your work, because it's very interesting. Compliments for the presentation.
Thank you very much, Professor Atanasio.
Thank you. Professor Ajala, do you have any additional question? Any remark regarding the document?
Yes, I have very few questions. And yes, the first one relates to the learning algorithm. I would like to know, according to the cutting process and the time you need to react, what are the concerns in terms of the quantity of data you need for the training before you can make a decision? And what will be the impact on the decision process?
Okay. If I understand well your question is how much data do we need before we can take a decision under the tool replacement, and how much time in order to make this decision?
Yes, that means how much data needs to make sure that the model you obtain has a good accuracy.
Okay, so we worked on that, and one first element of response to your question is shown in this slide, where we have indeed the we can assess through this slide also the convergence of the Cox-PH model In this case, it is working simply on the cutting speed parameters, but I showed on one of my contributions that with something like 25 to 30 points of data, we have already something that allows the Cox pH model to run without 5% of its converging value. So we have already some answer to this question, and this was used in particular in the decision of the number of inserts that would be worn in the experimental value, in the experimental work. It was part of the process in taking this decision. So basically, you would need to wear out maybe 30 inserts experimentally before you are able to start using the model, the pH model. I'm speaking here only about the pH model industrially. But what's interesting with that is that you can teach the model while continuing your production. So you just continue producing as usual, and through the process that I explained earlier, you just start by teaching your model separately. You are not taking the output of the model first, but you are taking either the logbooks I was talking earlier with Professor Pintelon, or taking the data as it comes, and after 30 inserts were worn, you start to have results from the Cox pH model, and you update your prediction with the time.
That's very interesting. And from your opinion, do you think that it's possible at this stage, in the framework, for example, of the Industry 4.0 context, do you think it is possible to react on the system and using your model to extend the life of the tool? Because I guess if you are able to adapt the parameters, the cutting parameters during the cutting in real time, maybe you can avoid some breakdown and so on. What do you think?
Yes, I understand you. So your question, if I understand it well, is whether we can use the methodologies that I developed in order to tune the cutting parameters in order to prolongate the tool life. Is it correct?
Yes.
Okay. Well, it is an interesting question, because you are taking the reverse point of view from the point of view I had on the thesis. My point of view is keep the parameters constant and work out from the parameters and the process as it is in order to determine the remaining useful life of the tool. So it is a very interesting question. I think there are already ideas that are worked in the industry. For example, one sometimes take tools used in finishing and use it in rough machining, because they are too worn in order to produce quality in finishing, but they are still able to machine for rough work. So it is a lead, but it's of course not using my methodology. I think, yes, you could adapt the cutting parameters, but you need to keep in mind that usually we take the cutting parameters corresponding to a catalog entries. So most often we are already using the cutting tools as close as reasonably and industrially possible to the optimal value regarding the tool life. So it's already quite the case now. If you wanted to do that, yes, you probably could, but keep in mind that usually prolongating the tool life comes by setting depth of cuts that are less steep, cutting speed that are slower, and so on, and that by taking less severe cutting parameters, you will also increase the machining time. So I am not sure that all in all, we are gaining much on this.
Okay, thank you. And I would like to congratulate you for all the job you have done. It's very, very interesting and very important. And okay, so I have finished. Thank you.
Thank you very much.
Okay, thank you, Professor Agela. Professor Roger Serra, do you have any additional question?
Yes, thank you, Chairman, to give me the floor. Okay, first I want to repeat my thanks to Professor Pierre Desombreux and François Ducobu for the invitation, and thank you very much. And second, I want to congratulate Luca for the quality and the quality of the report we have said, but the clarity of this presentation, because you have taken into account some comments, and this presentation is very clear. And just some remarks about the outlook, and not a specific question, but you have said probably you need to investigate some other non-stationary gamma process. Have you in mind, have you tried, or have you in mind some methodologies?
I'm afraid I didn't have time to look much into that, but the idea regarding this question is simply to look for other analytic expressions that would better than the one that I just show on this slide, analytical expressions that would better match the experimental evolution of the tool wear. It is indeed a complexity with this model, but I sadly did not have the time to look much into that.
Okay, and the other remark is about the overall approach. You in the data, we have only one data, is the wear, tool wear. If we imagine that we have a tool with many inserts, how or what is your recommendations about the application of the approach? Could we use overall approach in the same time, the same topic?
Are you speaking specifically of the stochastic approach, or are you speaking in general?
In general.
Well, in general, we are not limited to the measurement of the tool wear. Obviously, we took more measurements than that. So, but what's interesting, and especially with the pH model, is that you do not have to base your replacement decision. You do not have to base the tool end of life as you document it in the database from the tool wear. And this is interesting because if you decide to replace a tool because it's producing bad quality, then you can specify your tool as being failed in the database. The Cox pH model will take this into account as a failed tool, although maybe it did not reach a wear criterion.
Yes, okay. Okay, now thank you. No more question, no more remark. Thank you very much.
Thank you very much.
Thank you. So I will ask Professor Edouard Rivière if you have any question. Edouard.
Okay, so at first, thank you, Lucas, and I still want to congratulate you for the job you made during this thesis that combines scientific and technical work, which is not always that easy. We already had the opportunity to discuss about a lot of things. Maybe I have one last, I don't know if it's a question of a remark, but having your thought about one thing. The approach you developed during the PhD thesis can be interesting for three categories of people. The tool maker, the people that make machine tools, and the plants that work in production. What is your feeling about the people that you may at first contact to go further on the thesis? Considering that they may have some difference in goals and also in availability of data?
It's an interesting question, but it's also very broad. It's complex. I think indeed you gave part of the answer in the question. The question is mostly the availability, not only of the data but also of the persons. It's always complicated indeed. I have already contacts, as you know, with a machine tool manufacturer in the area. And it may be a lead for further work. Obviously, we also have contacts with machine tool users in the area, and I think it would be the next step before continuing the process with a machine tool manufacturer to go and validate the approach on industrial data by with the machine tool users first.
Okay, thank you. And maybe thinking about the sensor that can be put by default on machine could be an interesting trend.
Obviously.
For this 4.0 approach. Okay, so thanks a lot. I have no further comments.
Okay, thank you. We can finish now with Professor Pierre de Ombreux, supervisor of the thesis. Do you have any question?
No, I don't have any questions. Thank you very much for the clear presentation. And so maybe I will have some words of comments after the deliberation. Thank you.
Okay, and last, Professor Ducobu.
Thank you, Georges. No, I don't have any question. We had the opportunity to discuss during the last year about the very different topics, and so today I don't have any question. Thank you.
Okay. Thank you. Thank you, Luca, for this.
Mr. Chairman, we have one question from the YouTube audience.
Okay.
But sorry, I cut you. I think it's time for your questions. I just wanted to tell you.
I don't have any question.
Okay, I'm very sorry for that.
Okay.
There is one question from the audience, Guillaume Soudan, asking a societal question that I'm translating on the fly.
You can reply in French if you want.
Okay, the question in French is: comment l'impact d'une telle technique de remplacement des outils pourra être mise en place, pourra être mise en avant, face à un probable sentiment de perte de considération pour les opérateurs, à la fois dans leur expérience et dans leur sentiment d'indispensabilité pour le fonctionnement de l'entreprise. C'est une excellente question. Je pense que pour toute avancée technologique, c'est une question qui se pose systématiquement. Clairement, je pense qu'on peut mettre en place les outils de communication liés notamment à tout ce qui concerne le lean manufacturing, c'est-à-dire faire un état des lieux avant-après, montrer les gains financiers, les gains en qualité de la réalisation pour mettre en avant l'intérêt que l'entreprise a à réaliser ceci. Pour moi, il est clair que la pérennité d'une entreprise est aussi liée à ses résultats financiers, et donc, quelque part, il s'agit de pouvoir mettre ce genre de choses en place. Et après, charge morale à l'entreprise de s'assurer que le personnel qu'elle emploie conserve son travail. Mais bon, il existe d'autres approches à ça. Donc, c'est une question intéressante, mais évidemment qui sort du cadre de la thèse. I don't see any more question on the YouTube feed, so I think that the audience does not seem to have any more questions.
Okay. Okay. If there is no additional question, you just know to go to deliberate. To the member of the jury, I send Sunday an email with the correct link for the deliberation, which is not the same link that the one sent by Luca. So please use the link in my email. And so we'll go now to a private session to deliberate, and we'll go back. Okay.
To the few, oh no, okay, that's all right. You cut your microphone, so it's okay. But you maybe want to leave the meeting Jitsi. You will come back to this page later. Voilà, donc on est juste entre nous, en direct sur YouTube. Je vous remercie pour votre soutien. Maintenant, voilà, les questions, les commentaires sont ouverts. Je vois tous vos messages de félicitations. Je vous remercie beaucoup, mais rien n'est fait encore. Donc, attendez, attendez comment dirais-je, les résultats pour me féliciter. Mais en tout cas, ça me touche beaucoup et merci, merci pour vos messages. J'espère que le direct s'est bien passé, qu'il n'y a pas eu de coupure, que le son était compréhensible. Et voilà. Je vais couper la caméra et le micro quelques instants pour aller chercher un verre d'eau et je vous reviens dans une toute petite minute. On verra le temps nécessaire pour que le jury délibère. Je reviens tout de suite. Me revoilou. Merci pour tous vos commentaires. Si vous avez des questions, des commentaires, tout ça, voilà. Mais, merci à tous. Je vois beaucoup de noms et que je connais bien. J'en vois même que je connais moins bien. Non, je connais tout le monde. Mais en tout cas, c'était vraiment très sympa d'avoir du monde comme ça pour me regarder. Merci beaucoup d'avoir été présent en nombre. Génial. Alors, vous n'avez pas la possibilité de faire de hola de votre côté. Mais on la fera par Skype peut-être plus tard lorsque le jury aura délibéré. Et j'ai naturellement, et surtout je tiens à le dire, j'ai une pensée pour ma filleule qui me regarde et voilà, qui me manque beaucoup. Alors, super question de la part de Giuseppe. Oui, à mon avis, c'est quelque chose qui est applicable d'un point de vue maintenance pour l'estimation du temps de vie résiduel d'à peu près toutes. Donc, la question, je vais peut-être la répéter oralement, c'est est-ce que je pense que la méthode peut être modifiée, extrapolée à des procédés industriels qui ne sont pas en lien avec l'usinage? Donc, c'est une question super intéressante. J'ai pas eu le temps de m'y intéresser dans la thèse parce que le sujet de la thèse était limité à l'usinage, justement, et encore au tournage, même si on va aller plus loin. Enfin, quoique. Maintenant, pour répondre à la question, donc non, je ne pense pas que ce soit limité à l'usinage. La méthode statistique qui est derrière, elle peut très très bien s'accommoder d'un tas de données de défaillance. La difficulté toujours, que ce soit en usinage ou ailleurs, c'est d'identifier les bonnes variables de condition monitoring et de pouvoir, on va dire, avoir une idée sur l'estimation des charges qui vont s'appliquer au système par la suite. Donc, clairement, ça va plus loin que juste l'usinage.
is on.
Ah, voilà le retour du jury.
Is on.
Okay, Luca, we are back. It was a quick deliberation. All the members are here. No. Okay, François, I see. Okay, all the members are here. So, Luca, after having deliberated, I have the pleasure to carry out the final decision. I will give the final decision in French for legal reasons. Après avoir pris connaissance de la thèse déposée par le candidat, après avoir entendu le candidat en séance privée, après avoir conclu à la recevabilité de la thèse en vue de l'obtention du grade académique de docteur en sciences de l'ingénieur et technologie, le jury, réuni sous ma présidence, a entendu ce jour la défense publique de la dissertation originale, après quoi il a décidé à l'unanimité de conférer à M. Lucas Equeter le grade académique de docteur en sciences de l'ingénieur et technologie. Congratulations, Lucas.
Congratulations.
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 Merci beaucoup. Merci.
So, after this deliberation, usually you have a drink, but there is no drink. Maybe a e-drink, but before we have the supervisor usually take some time to congratulate the candidate and give some words about him. So Pierre, if you have, and François, if you have something to say.
So thank you very much, Mr. President, dear colleagues, dear friends and members of the audience. So despite of the strange circumstances that kept us away from each other, we are meeting today to celebrate scientific and technological progress with the contribution of the PhD of Dr. Lucas Equeter. I am particularly proud to congratulate him personally, considering his remarkable career in the Faculty of Engineering. The first souvenir of Lucas dates from his project in mechanical design, where he was in charge of the design of a pipe inspection robot, and he already demonstrated his skills in design and in engineering, and we were lucky to recruit him as an assistant 1 year later. At that time, so 4 years ago, Lucas immediately impressed the maintenance and reliability team, composed by Christophe Leteau, Arnaud Lesage, Guillaume Florquin, and some others, with a deep insight in the evolution of maintenance challenges. He was at that time engaged in a study of about opportunistic maintenance, because it was his master thesis subject, but he decided to grasp a subject in the intersection of research field of the machine design and production engineering lab. And so 4 years later, Lucas was able to produce an impressive work dealing with analytical, numerical, and experimental issues that is not so common. So considering the high workload in the unit that is shared among the professors and assistants, because we have more than 100 students in mechanical engineering that are supervised for their design project, industrial internships, and thesis. So due to its high pedagogical workload, it's an outstanding performance. So I just add that Lucas was also engaged and still engaged in the scientific life of the Faculty of Engineering as a representative of scientific staff and animator of numerous discussions about PhDs. So je passe peut-être en français maintenant à l'intention du public large qui nous a rejoints sur YouTube et que je remercie tout particulièrement pour l'intérêt qu'il porte à nos travaux et aux travaux de Lucas. Donc j'ai simplement dit que la contribution de Lucas était décisive et impressionnante, considérant qu'il n'a pas travaillé uniquement à temps plein sur son travail de recherche, mais il a beaucoup contribué aussi à l'encadrement de nos étudiants. Donc voici, Lucas, une étape dans un parcours marqué par la curiosité, l'appétence pour de nouvelles expériences, un engagement scientifique, technologique, social, qui font finalement la richesse d'une vie universitaire. Lucas reçoit toutes nos félicitations pour ce parcours que tu as construit avec passion, engagement et intelligence. Voilà une étape de franchie et conçois donc les suivantes avec la même énergie qui nous vaut le plaisir de bénéficier, de partager ton enthousiasme. Bravo et félicitations. Alors j'aurais aimé vous inviter tous au verre de l'amitié. C'est malheureusement impossible aujourd'hui, mais chacun aura quand même l'occasion de lever bientôt un verre à la santé de Lucas. Ne soyez quand même pas inquiets. La durée de vie résiduelle du Covid-19 se réduit aussi inéluctablement que celle des outils de coupe, même si les constantes de temps se mesurent davantage en semaines qu'en minutes. Alors l'Université de Mons et sa faculté polytechnique poursuivent leur mission de recherche, d'enseignement et de service à la société avec beaucoup d'énergie. Et la présentation d'aujourd'hui a démontré que nous pouvions nous adapter aux circonstances les plus sévères. So I especially thank the members of the jury for their involvement in this PhD process, and I invite them to meet all together in Mons as soon as possible. Donc je vous donne rendez-vous à Mons en des temps meilleurs pour célébrer la thèse de Lucas et lui adresser collectivement nos félicitations de manière directe. Mon cher Lucas, bravo, congratulations.
Merci.
Merci.
Thank you.
Merci,
Pierre.
Pierre.
Okay, Lucas,
Mr.
do you have
Chairman.
Any comment, anything to say to close this session?
I obviously have stuff to say before we close the session. Obviously, I want to thank and to acknowledge everybody who was involved in the thesis. And when I say in the thesis, I mean from every perspective. Obviously, I cannot say how much I thank Professor Dombreux, Professor Ducobu for their help, their listening ears that was always available when in doubt. And there were numerous moments where when doubt was introduced in this thesis, but we always kept the right direction, and this is thanks to you. Thank you very much, Pierre-François. Merci. Et pour tous les autres, I will switch to French because it's more personal to the persons I will now address, aux étudiants avec lesquels j'ai passé des heures assez incroyables à cause effectivement de la surcharge de travail, mais aussi et surtout parce que c'est notre plaisir et c'est notre travail et qu'on le fait avec passion. Eh bien, à nos étudiants, merci. À ma famille, bien sûr, qui m'a toujours soutenu et poussé. Et surtout à Lucas qui partage ma vie et mes difficultés. Et voilà, à vous tous, merci beaucoup, merci infiniment. Et surtout, merci à mes collègues qui ont supporté ma mauvaise humeur parfois et comment dirais-je, mes doutes, mais aussi mes espoirs tout au long de cette thèse. Merci à tous.
Okay, merci Lucas. Thank you, Lucas. So, I suggest now to close this session. There's nothing to do anymore. Again, congratulations, Lucas, for your work, for this presentation. And I hope to see you again soon. To the member of the jury, thank you.
Okay, thank you all.
Thanks.
Thank you so much. Thank you, everybody.
Okay.
Thank you, dear colleagues.
Thank you.
Thank
Bye.
you.
Thank you. Bye-bye.
Bye-bye.
Bye.
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 Congratulations, Lucas. Bravo.
Merci, merci beaucoup.
C'est prochaine étape. C'est qu'une étape. Et là, c'est toujours dans la prochaine. Mais profite.
Lucas, tu es encore avec nous?
À un moment, il faut profiter.
Merci, merci. Je
Et
vais
en
tâcher
attendant-
d'en profiter.
Et oui. En attendant de trinquer.
Merci, merci, merci.
À bientôt et au plaisir de vous revoir. Hein.
Merci,
À
au
bientôt,
plaisir.
Roger.
Oui, j'espère bien, j'y compte bien.
Portez-vous
Voilà,
bien.
donc je vais clôturer le live YouTube. Merci d'avoir été nombreux à nous regarder. On a frôlé les 70 à un moment, je crois. Je regarderai les statistiques plus tard, mais c'était vraiment un plaisir et je vais essayer de répondre à chacun de vos commentaires de félicitations. Merci à tous.
Voilà, merci et profite bien maintenant l'après-midi.
J'y compte bien.